Greetings, Matthews. If you're watching this, it means that something terrible has happened. Well, maybe not that terrible, like my kid's sick, or maybe you're just rewatching it to remember what the heck functions are. Because we are starting a new unit. It's a new dawn, it's a new day, it's a new life. And so we're looking at functions. I think you've seen functions before. Functions like describe the world around us, and they don't all behave the same way. So we have to pick and choose which functions. And the function is just an equation with a little twist. It's more specific than an equation. So, we've seen functions like this, y equals mx plus c, and they make straight lines like that. And that's good for describing like constant motion, no acceleration, like maybe a car going at a constant rate. And oh no, this one has a higher slope, right? So it's going faster, like that, right? They're still just lines. Okay, fine. But maybe that's not appropriate for throwing something up in the air, because that's not a linear motion. It slows down at the top and then reaccelerates coming back down, and so its graph looks a little bit different, and so we have to use a different function, quadratic, to describe that. Yeah, get your head out of the way, Gorkevich. Get your head out of the way. There. Okay, so functions. They're just like little equations with a twist. Now here's the twist. There can be lots of different ways to connect values. And any connection between one set of numbers and another set of numbers is called a relation, like a relationship, right? Functional relationships. And you guys are good at relationships. It's not you, it's me, realizing that you're terrible for me. Relationships, right? You guys are acquainted with relationships, and so there might be some connection between like this number and that number, this number and that number, this number and that number, right? X's and Y's. Sometimes there's a relationship. Well, there's always some relationship, and so we call that a relation. If there's a very systematic relationship that I'll show you in a second, we call it a function. Now, we can show these relations in lots of different ways. We can show them with ordered pairs. This is the exact same set in a table, and this is the exact same value in a graph, and this is exact same value in a mapping setup. Yeah, mapping, they're all just similar ways to show the same thing. Now, and so here's 3, 1, 3, 1, here's 3, 1, here's 3, 1. Yeah, not a problem. You'll notice that this one is a little bit chaotic, because like the X's don't always give out the same Y values. Like sometimes I put in a -2 and I'll get out a 2. And sometimes I put in a -2 and I get out a -2. I don't like that. So this is problematic, where one value gives you two different outputs. This one makes mathematicians feel like that. This second relationship down here is a little bit better, meaning that it's more predictable. So this 0 always gives you a 2, 1 always gives you a 3, and they're repeated there, and hey, look, they make a nice little graph, and here's the mapping, nice and clean. This one isn't a problem. We'll talk about that in a second, because it's still functional. But the difference between these two are they functions or are they not functions? And we'll talk about why that's important. So, I don't know, shameless photo time. That is my boat going through the Panama Canal. And we went through with these two little sailboats, other sailboats, they're not little, they're 40-foot sailboats, stuck to the side of my boat. And they charged our boats the same, even though my boat's a little bit wider, right? Because I was a catamaran, and these are a little bit narrower because they're monohulls. They charged us the same amount to go through the Panama Canal based on weight, right? And that's good, because well, it costs about $1,000 to bring your sailboat through the canal. It costs about $1 million to bring one of those big shipping ships through the canal. And so there's like 6 locks. And so sometimes we were in with these big boats and they would charge those boats quite a lot more. And it wasn't based on length or width because my boat was wider. It was based on mass. And so if you look at the Panama Canal, they take the mass of your boat and use that to calculate the fees. Yeah. So that kind of makes sense because a certain mass, if you took like the mass of your boat and the cost to go through, they should be the same. And I don't know, it doesn't even need to be linear. It could be like something like this, and they really go after the high-end boats. But the thing is, if my boat weighs 24 tons, then I'll pay this much. And if your boat weighs 24 tons, you should pay the same amount. When you put in 24 tons, it should give you $1,000 out as the cost. But if our boats weigh the same and you pay 1,000 and I pay 500, it means that you're bribing somebody or something, right? So the same input one input should give you always the same output. Here's a couple of examples of that. So this is like functions are relations where an input always gives you the same output. So maybe relationships like the temperature of your soda over time in the sun, right? So here's time, nope, little t. And here's temperature, and whatever it's warming up, right? So it's going to do something like this, right? And at a certain time, at time 10, your soda should be a certain temperature. If you put in 10 again, you shouldn't get a different temperature because then, I don't know, are you testing in 2 different spots? Now, it is not a problem. Like if we come up to, let's say the room temperature is, I don't know, maybe it's 22 degrees outside, and your temperature of your soda eventually comes up to 22 degrees, right? And at 30 minutes, it's up to temperature, 22 degrees. If you put 35 in and it also gives you 22 degrees, no one loses their mind. It's just up to temperature. And 35 and 36 and 38, they're all, when you put in those values into the equation, they all give you 22, 22, 22. Is that a problem? No. What is a problem is if you put in 30, and sometimes it gives you 20 for the temperature, and sometimes it gives you 15 for the temperature, that doesn't make sense. Okay, so one input can give you only one output. Here's something else that might not be a function. Maybe number of siblings and your test score, right? So this is number of sibs, and this is your test score. Well, maybe there are some of you with 2 siblings, and maybe some of you got a 5 on the assessment. And if I put a 2 in, I should get a 5. Great. Oh, but there are others of you with 2 siblings, and some of you got 7s on the assessment. This doesn't make sense because the 2 input gives you sometimes 7, sometimes 5. It's a relation, but it doesn't function well because we don't like that I put in a 2 and sometimes it gives me that and sometimes it gives me that. Okay. Maybe you're more relationship based. You could think about friends and biological parents. So friends, like maybe if our input is Amy, our output is Brett. And you're like, Amy, who's your friend? Brett. And you're like, hey, Amy, who's your friend? Bart. Hey, Amy, who's your friend? She doesn't like Laura. Let's go Philippe. Right? That's okay that you asked Amy, you put in A, and sometimes you get out B, Rhett. Sometimes you get out Bart, and sometimes you get out Philip. Right? You just keep asking, hey, who are you hanging out with tonight? Who are you hanging out with tonight? Sometimes here, sometimes here, sometimes here. Right? So if you ask A, sometimes you get out Brett. I should have picked a different. Sometimes you get out Bart, and sometimes you get out Philip. That is a relation. It's a relationship, but it's not a function. It's not functional because when you ask Amy, sometimes she gives you 2 different answers. So this is not a function. Function. Conversely, if you ask about somebody's biological mother, now I know that things are complex, but if you ask Amy, who's your mother? And she says, Brett. That's fine. That's completely fine, as long as that's always the same answer. You have to ask Amy, who's your biological mother? And if she says Brett, as long as she says it every time, then this is a function. Now, probably if you've experienced some biology, probably if we're talking about biological mother, it's going to be Laura. But there you go. What's this? Oh, there's some other things. If you ask a person for their social security number, they'll always give you that same number. If you ask a dog where its tail is, it'll always give you the same tail. Now, that's functional. Non-functional, just to give you some more examples, you can fast forward through this if you got it. A person could say, you could say, hey, what's your phone number? And that person could tell you their cell phone. And then if you could ask them again, hey, give me a number for you, and they could give you like maybe their house phone. Back in my day, we used to have house phones, right? Or maybe their address, because like I could give you my address here in Switzerland. I could also give you my address in the States. And so you can ask me the same question. I'll give you two different answers, and that's non-functional. Same thing. You're like, dog, where's your foot? And it's like, here. And then you're like, hey, dog, where's your foot? And he's like, here. And then, hey, dog, where's your foot? And he's like, here. You get the idea. Non-functional. Okay, moving on to the math. Oh, I guess not. This is sort of like a machine, right? And so the machine takes whatever your x is, does something to it, 2x plus 1, and kicks out a value. So if this is 3, it puts in 3, multiplies by 2, 6, adds 1, 7. So if we put in 3, we should always get out 7, just like a vending machine. If you push number 7, you should... Oh, there it is. You should always get out Doritos, right? And so if this is a machine, 2x plus 1, if you put in 3, you get out 7. So if at some point we put in a 3 and we get out a 10, something else has happened here. And it's like pushing the button, and sometimes we get Doritos and sometimes we get a squid. And that makes me feel like this, right? Right. So the idea is that it's behavior. We differentiate between just regular relations, and functions. Doesn't seem like it makes a difference, but these two are very similar animals, right? They have fins, they live in the water, fins, they have flat kind of tails. Basically, they're the same thing, but their behavior is very different, right? And so this one is going to chew your arms off, and this one is going to squeak adorably and throw a ball around. So it's the behavior that we're interested in. So if we say a function, and we use function notation, f of x, instead of y, this says every input you see is coupled to only one output. And when you put that number in, you'll always get this one out. It's behavior. There are other relationships that don't do that, but then we don't specify that they do that, so you know how they act to behave. Now, some of you can call things y, and any relation you can call y, you can call f of x, but not vice versa, right? They have to behave a really specific way. So let's try one out. Let's add a nice little function here, yeah. So we want to give some reasons. Are these functions or not functions, just based on what we see? So let's start with these. And this is just like as far as we can tell. So a -2 gives me a 0, -3 gives me a 3, and -4 gives me an 8, a 0 gives me a 0. Yeah, that's okay. I don't mind that this happens, because maybe it's like... I don't know, time and temperature. And we're saying -2, 0, and 0, 0, and -3, 3, and negative 4, 8. Negative 4, 8. Right? So maybe what's happening, just, I don't know, making stuff up, is our temperature looks like it's doing this. So maybe this is water. I don't know. It doesn't actually have to follow a pattern at all. It just needs to be, this always gives you the same value out. But maybe this is water cooling down, hitting 0, and freezes, and then it stays at that temperature for more time, right? And so it's okay that 2 different x's give you the same y. That is not a problem. And even if there's no relationship that you can see between them, as long as you don't get an x giving you 2 different y's. So this one looks like a problem. Sometimes I push the 5 button and it gives me -1. Sometimes I push the 5 button and it gives me 3. So this is not a function. This one is a function. This one is a line, right? 1, 2, 3, 4, and then -3, something like that. It's functional because every x that you put in only gives you that value out. So that one's a function. Great. Let's see if these are functions. Guessing some of them are and some of them aren't. This in A is not functional because sometimes you push, this is like a square root curve or something. Sometimes you push the 2 button and it gives you 3.5, 2 comma 3.5. Sometimes you push the 2 button and you get -3.5, and that is not functional. The way that we would make this functional is restrict the range. We'd say let's let r's be, let's let the range be just y's that are greater than or equal to 0, right? And then if we do this, then it becomes a function because you've restricted the domain. B looks okay. Like if you put in -2, you always get this out. If you put in -2 again, you always get this out. Except right here at 1, you put 1 in. Because this dot is closed, sometimes you get 1, sometimes you get 2 out. So that's not a function. The way to fix this, if we needed to, was make one of these an open dot. And then it makes it a function. These all pass the vertical line test, really, which say that this x should only touch 1 time on the function, and they all do. This one doesn't pass the vertical line test, right? This one passes the vertical line test, except right there where it's 2 potential spots. This, I think, does. It's kind of unclear. I guess as long as this isn't a dot, it looks like they leave this open so that right at 4, now you jump here. So function, function, not a function, not a function. Okay, moving on. We can also talk about domain and range that you've probably heard and hate, but it shouldn't be a terrifying thing. Domain is just like what x values are legal, and range is what y values are outputs, given that we've only put legal inputs in. So here, I kind of want to make this a line, but it's not a line, right? It's just this one and this one and this one and this one. So I think the domain of this thing is 2, 3, 4, and 5, scripty brackets, and the range is only 1, 2, 3, and 4. Now that's a little annoying, but if you wanted all of the points in between, then you would have to put all the points in between, and that just becomes a line. That's why we make the line. Okay. For number 2, it looks like the domain is anything. Like, I don't know what the equation is, but I mean, I do know what the equation is, but if we didn't know what the equation is, like, look, this doesn't look like, this looks like it could go on forever. There's no dots at the end or anything. So I'm assuming that it's going forever this way and forever that way. I wish they would put arrows on it. But the domains the domains are x's. If we wanted to be formal, we'd say the domain is the set of x such that x is in the set of all real numbers. Oh wait, except you never get this 2. So then you'd say and x's are not equal to 2, -2, close scripty brackets. And then the range is like, okay, if we play that game, what y's are you going to get out? This is like cool notation. If you wanted the shorthand version, you'd say x not equal to 2. This makes it look cool. So take it with a grain of salt. I want the y's. Looks like I can get anything out of here. Big numbers, small numbers, fractions. They're in the set of real numbers, means all the numbers, square roots, whatever. But I see that I'm not getting this. It doesn't touch at 0. So x can't be 0. Oh, sorry, y can't be 0. So you'd say y can't be 0, shorthand. Cool, long, cool way, impress your friends. Shorthand, I don't have time, moving along. Domain here looks like everything. X's in the set, x's are all real numbers, like everything. But I see that I'm not getting, I'm getting x's between here and here. So the x's are going to be between and not including, because they're using an open dot, 2 and -3. And the ranges is the y's, such that y's are in the real number set. Oh, we'll do that with this one in a second. But I'm only going from -5. I want y's not equal to -5, but from -5 up, open dot, right? I'm looking from here up to here. And I see that it does maybe hit 2 right there. Now going back to this one, we could write this again like this. We could say the x's, the domain is the set of x's such that x is in the set of integers, right? Then you only get 2, 3, 4, 5. And I want my x's to go from inclusive to 5. Or if you really want to be cool, 1 to 6, not inclusive, because they have to be integers, right? Either of those would work. This one's annoying, right? And then the range is the same thing. The y's such that y's are in the set of integers. And I want to go from 1 to 4. So you go from 1 to 4 inclusive. It works. Similarly, the domain is going to be the set of x's, so from 3 to 1, so x is such that x is in the set of all real numbers. It's all real numbers because we have all these little connected dots, and I want x to be between -3 and 1. I'm using this as inclusive because these are closed dots. And the range the same way, y such that y's are in the set of all real numbers. And I'm going from -4 up to 0 inclusive. What? Ooh, too much zoom. Okay, so you've seen quadratics. That's one of the ones we're going to focus on first, just because you've already had some experience with them, and you've seen this as their standard form. Ax squared plus bx plus c works great in physics. X and y are the variables because one is like time and the other is like height or whatever. They're the things that vary, that change. And these parameters, the a, the b, and the c are called parameters, and they change the shape of it. You've seen that before. Right? So based on the A term, we get a like wider. Based on the C term, it slides up and down. The B term is some weird hybrid. We'll talk about that later, but I want you to know this word parameters because it comes up. We can call this thing a degree 2 polynomial, and that's nice because then if you have something like this, this is the highest power on the whole thing, so this is a degree 14 polynomial. Yeah. So there's a couple of different scenarios. Ooh, why aren't you going? There's a couple of different scenarios with the different forms. This is standard form. This is useful in physics and stuff like that because that's acceleration due to gravity. This is initial upward velocity if you're firing a ball, and this is the release height from that you're throwing something from. That's fine. Sometimes we like vertex form, which looks like this. And we find this by completing the square, if you remember how to do that. And this tells you H and K, tells you the vertex, and so that's useful. And we also like factored form, which is this, or intercept form, or zero form, where this and this tell you the zeros. So like this, it's easy to graph because it would be x minus 2 and x minus 4 with some a term that we could figure out. And what's kind of cool is that in all of these, as you switch from one to the other, the a terms are always the same. They don't get modified. It's just the rest of it. So this intercept is also called factorized form, etc. You'll notice that when it's concave up, it's like it's catching a cup, like catching rainwater. It looks positive because it kind of looks like a smiley face, a crazy smiley face. A term is positive. So as you go over, you're going up, over, up, over, up. Same thing with this. If it's concave down, meaning upside down, pouring water out, the A term is negative. Makes sense because you go over and then down, over and then down, over and then down. And it kind of looks like an angry face, so that works. Okay, so let's try a couple of these. Axis of symmetry and things like that. I think you've seen we have an equation for axis of symmetry. It's in your formula booklet, but really it comes from the quadratic formula. Quadratic formula says if you want to find any x values, roots, intercepts, zeros, if you want to find these, start at the axis of symmetry. I guess if we rewrite it, there it is. Start at the axis of symmetry here, and then go one direction, and then go in a positive direction this much. Zip. How much is that? I don't know. Or go in the negative direction that same amount, right? And you'll find the two zeros. So we can just steal this stuff off the front and realize that that is this axis of symmetry. Okay, so one way to run this, here's state the concavity of this function. Well, a term is negative, so it must be concave down. So our graph looks like that. Great. Find the equation of the axis of symmetry. Well, we can just use this and say this thing is B, this is A, so I had to do a little zooming. So here's B, it's 4 over 2A, so negative B over 2A. The negative comes from here, and so the axis of symmetry is 1. Okay, great. They asked for the vertex. Well, I know wherever this thing is, the middle is at 1. It's upside down, so this is at 1, and the height is determined by this equation. So what we can do is take our 1. We know this is 1 comma I don't know. So put the 1 in there and there. And so that's what we're doing here, is we're finding f of 1. So instead of calling this y, I called it f of x. It means into the function I'm putting some x's. And so f of 1 means put a 1 in for those x values. We clean it up, you end up with 3. So the intercept, or the vertex, is at 1 comma 3. Okay, domain and range of this thing. Well, the domain is going to be is anything, because I can't think of anything I could put in this equation that would be illegal. So like, I don't know, you could think about square roots. The square root shouldn't be negative underneath the radical. The radicand should be positive. But in this quadratic, I can't really break it. You can put negatives in those x's. You can put fractions and decimals, and nothing's really going to break it. So all real numbers. But the range is only going to be from here down, because I know it's upside down. So the range is going to be y's such that y's are less than 3. There's some other cool notation that you might see like this, y such that it goes from, maybe this should be negative infinity to 3. And they say include 3 with the bracket that's facing 3. And they say exclude negative infinity because you can't get there. It's not a number, it's a concept. So, or sometimes you see this with square brackets with a 3 and the roundy brackets and the negative infinity to say don't include, don't include. I prefer this. I think it's more transparent, but I think you can use these notations. I just think they're clunky. And then D, the vertex form of the quadratic equation. So this is the H and the K, so we can just plug them in here and here. Another way to do this is complete the square on this piece. And completing the square is a technique that you've probably seen. Maybe, yeah, I'll do it here just so you can see it. And if you're like, I know how to do it, or I'm never doing that again, then feel free to fast forward me. But just for the sake of, being solid with this. Okay, so with completing the square, you try to take this little 1, move him out of the way like an annoying little brother. He doesn't get to play right away. I'm going to factor out anything that's common in here. And then I'm going to think about what would make this a nice perfect square. Ooh, there's X still there. I would really love it if this on the inside was x squared plus 2x plus, take this middle part, cut it in half, and then square it. So 1 squared is 1. So I did this, so this middle part would factor down to x plus 1 squared, because that's what vertex form looks like. Now, the problem is I just gratuitously added 1. So I have to subtract, I have to undo that on the outside. Oh, but I did that, I had -2 of these. So really I added -2, so I really have to add 2 to the end. You see, this is really -2, and so I need to add 2. So this -2 is still sitting here. These become 3, and that's the same vertex that we had before. Somewhere, you can fast forward. Cool, so that's completing the square, and in some cases, that's easier to find the vertex, because bam, bam, there's the vertex. Where's the axis of symmetry? Right there. Neat. Impress your friends. So, I don't know, some guru comes into your bicycle company, calculator company, and says that this is the profits based on the numbers that you sell. And so, like, as you sell more, yes, maybe you gain more cash, but also maybe there's more like distribution costs to you and material costs. And so it's not always going to be linear, right? So it's going to do something like this. You can kind of think about t-shirts, right? Like if you have a really cool t-shirt design and you charge $1,000 for your t-shirt, no one's going to be dumb enough to buy your t-shirt. And if you give them away for free, you're not going to make any money. But somewhere in the sweet spot, you can start charging more and more, and people will still buy them. Eventually, if it's too much, people stop buying them so much, and there's a sweet spot. And you can maximize these profits if you can kind of see how much you lose every time you increase the price. Okay, so let's maximize the profits. I know this is negative, so it's flipped over, and it's starting down here, so it's going to look like something like that. We want to find the selling price that generates the maximum profit, and this is the X value, and so it should be right at the top. So what we can do is use the vertex I don't want to complete the square on that. So let's find the vertex using negative b over 2a, and ends up being 35. We steal b and a, and then we put the 35 into the function itself, and then find the profit. Cool. All right, last one. We want to be able to model functions, like make an equation that describes them. So if we have this data set here, and I know this is true and this is true, and here's a vertex, and we try to build an equation, we could choose any of the equation types, right? We could choose standard form. I don't know. We could try intercept form. Do you think you can find that intercept? I can't see that with my old eyes. Oh wait, vertex form. There's the vertex, easy peasy. So take the money and run, steal that vertex form, and let's fill in what we know. I know the vertex is at 3, 5, so we're going to use 3, 5 in the H and K, and it turns into 3 and 5. Right? Now the problem is I don't know the A value, but I have some other landmarks to help me with that. So we could substitute in any point. I'm going to choose 0 and negative 4, this one. I'm going to, with the 3 and the 5 that I do know, and say, okay, since I have an x value, let's put that x value in here. I should get this negative 4 out for the y value, and the only thing I don't know is a. Little substitution, little simplification. A is negative 1, and so there's our equation. Similarly, if we're trying to make an equation for this fancy mess, we could do the same thing. Let's find the vertex. It really looks like it's 8, negative 1. But because they didn't tell me that, I'm going to go ahead and play the game and pretend I don't know that. Maybe it's true. But if they don't put it on there, it might not be the case. So the fact that they put this one and this one and this one on there means those are legit. And that seems like, that we should use the intercept form because they gave us intercepts. And so we know the intercepts are 3 and 1. So we can use 3, negative 3 and positive 1. Note that it kind of flips the signs around. You can think about solving a factored equation about why that works. And then we're like, okay, well, that's nice, but I need that A term. We can pick any other point we're confident in, 0 for x, negative 6 for y, and plug them in, substitute them in to this equation for x and x. They can get the 0. There they are. And y can be negative 6. And when we simplify and solve for a, you get 2. And so you plug that a in with the rest of the parameters and leave x and y as variables. Cool? Okay, there's a handful of problems that you can mess with about the functions. Give that a shot, and I will see you soon.